I'm going to be talking about hierarchical charts. I'm going to talk about how to build hierarchical charts in Semiotic. For those of you who are joining me, if you ever have any questions, if you have any questions about how to use Semiotic, how to build a particular chart in Semiotic, or more general questions with D3, I can see I've already got one comment. That's good. If you have any questions, if you have any comments, let me know. Like if, I've got plans. We've all got plans. We all had plans with our lives when we were young. I have plans. My plans today is to look at hierarchical charts. But really, as I try to say in these streams, if there's something other people want me to look at, if there's some kind of example or particular data set that you want me to dig into, either in this stream or in a later stream, just let me know, and I'd be happy to get into it. I'd be happy to talk about how to do more general D3 stuff, how to do more of the React integrations, the lifecycle events and things like that. I want this to focus on Semiotic, but Semiotic exists in this ecosystem where D3 and React are major players. So that's how things get better. That's how I'm going to get better at making this stuff. That's how I'm going to make a better framework. And also, I'm just going to have a more fun time. So with that in mind, I want to talk about hierarchical charts. And I want to get into setting up a hierarchical chart in Semiotic, which is pretty fast and easy. So I've got this hierarchical charts tab over here that says hierarchy, all the things. This is from this Semiotic examples repo, which I'll post a link to in the chat. And also I'll post a link to the actual Semiotic interactive documentation in the chat so people can jump on that if they want to. Take a look at the interactive documentation. You go click on the hamburger menu over here, and over in the hamburger menu, if you go down to network frame, for some reason it closes that little hamburger menu the first time you do it. There's a section called dendrogram. Dendrogram was because originally I was only implementing dendrograms in Semiotic, but then I decided to implement all of the sort of standard D3 hierarchical charts. So that's tree maps and partitions and cluster diagrams and circle packs and things like that. So you can take a look at the code down there. Here's the code that we'll be working with, or the kind of code that I'll be writing, and so on. But real quick, for those who are following at home and for whom I sort of gloss over certain things. So Semiotic examples is a repo. You can clone this repo locally. And then if you clone this repo locally, I'm just going to do this real quick. Clone this repo locally into whatever directory you did. I unimaginatively put it in a Semiotic examples directory. And then you hit npm I. That'll install all of the modules that this needs to run. So that includes React and all the Semiotic stuff and any extra libraries that I use to process data and things like that. And then after that, after you hit npm I, it should install everything just fine. You can do npm start. Now you'll have to have npm installed, you'll have to have node installed and things like that. And I can't get into sort of the ins and outs of getting all that set up. But once you have all that set up, literally this is all you have to do. You hit npm start, like any sort of React create app, it'll start you out on the home page. In this case, the home page will look like this. And it says a home page. It's very unimaginative. I should probably at some point spend some time doing some design work and making this more fun. And it'll give you all of these tabs that'll correspond to different components in that repo. So over here, those components over here are like this bar chart component and this climate dashboard component and this hierarchy component and so on. And that's actually the code that's running these data visualization examples. Some of them are quite involved, like this, like what I called that climate dashboard example. And some of them are less involved, like this simple icon bar chart, a diverging icon bar chart. And then there's an example showing you how sort of robust annotations work in Semiotic. and how I make fun of Pokemon sometimes. Annotations, the Sankey diagrams. We'll get into the hierarchical charts. This various tab was just a place where I was really just doing a bunch of stuff, from simple scatter plots to line charts, and a very long OR frame that was showing the distribution of alcohol by volume of various beverages, and then this fun little bar chart of baseball players and their salaries. And then the other ones over here, the responsive donut chart and the line brush, are just for sort of individual examples that people requested that I wanted to get into. So that's everything that's available for you. Let me just adjust get rid of some things. There we go. So semiotic examples gives you a lot of the code, so you can see how to do these things that I try to live stream. Another way to get into the code is you could clone the semiotic repo itself, right? And you could go look at the docs. So if you go look in source/docs, you'll see all of these docs components. And typically what you'll want to look at is the raw version. So Swarm Brush Raw will show you the OR frame settings to set up that swarm brush or whatever. Now all of the code is in the, I try to put all of the code in the interactive examples, but sometimes there are certain effects that are hard to follow that you might want to look at the actual code and not just what was pasted into the examples. Okay, so let's make some hierarchical diagrams. Here we go in hierarchical charts. There's nothing there. If you want to follow along at home, I'm going to be in this hierarchy component, and anything I change in this hierarchy component, like this, is going to update that tab. So I'm pulling in two data sets here. I'm pulling in this baseball data, which I was working with yesterday, and I'm also pulling in flare data. The flare data is sort of your traditional hierarchical data sets. Let's take a look at what that looks like and talk about hierarchical data a little bit. Oops, flare data. I thought that was going to autocomplete. More tools, dev tools. Flarty data is not defined. Well, that's not true. All right. So flare data, I'm obviously logging a lot of different data sets throughout this whole thing. What's a hierarchical data set look like? Well, this is what it looks like. It's an object, a hierarchical data set, hierarchical JSON. When people refer to that, they refer to a JSON object or a JavaScript object. And that JavaScript object defines a hierarchical data structure. So in this case, it's something with a name, and then it's something with children. And so in this case, it's name. The name indicates what level of the Flare API you're at. And so Flare is a library that was one of the original sort of data visualization libraries built for, I think, Java originally, and then ported all over the place. And so it has this typical nested structure that you see with older libraries. So Flare has all of these subcomponents, viz, analytics, animate. These are going to eventually expose functions that are important for data visualization. So if we go into viz, you can see that viz also has children. And one of those children is called visualization. And visualization is actually some kind of function of a size, right? But it also has a child component, axis, and axis has children. Axis's children are all of these functions that have finally a size. That size has a, and in this case, size is indicated by value. That's the size of the actual function in lines of code or whatever, right? And so you can think of a lot of things that have hierarchical structures like this. Family trees might have hierarchical structures like this, depending on how you expose them. Directory structures most definitely have hierarchical structures like this. And then there are things that don't necessarily have hierarchical structures, but that you can nest and make hierarchical. using tools like D3Nest or using your own sort of custom tools for nesting. The fundamental aspect to hierarchical data that you have to keep in mind to distinguish it from other types of network data is that hierarchical data has to have every element has to have either 1 or 0 parents, and you can only have one element that has 0 parents. So you have one element, let me just say that a couple of times, you have one element, flare, that has no parents, and that's considered the root node. And then you have lots and lots of elements underneath it that can only have one parent each. And so in contrast, you could have networks where nodes have multiple parents. That's what that would fall under what's called a directed acyclic graph. Or then you could have networks where there wasn't any distinction, sort of child-parent distinction, or no directionality to the network. And that's what you would use sort of more traditional network visualization techniques like force-directed network layouts. So we've got this hierarchical network, and what distinguishes Semiotic from a few other libraries is that there are, if you're familiar with Semiotic, if you've seen any of these before, if you haven't, by the way, and you want me to get into some of the core details of the project, I'd be happy to explain those. But for now, I'm going to assume that either you've seen other ones or you've read up on it or whatever, and so you're aware a little bit of the abstractions that Semiotic puts in place. In Semiotic, there is no sunburst chart. There's no tree map chart. There's no bar chart or pie chart or anything like that. There are 3 different kinds of frames, and a frame is just a sort of, it's a component, and it's a component that represents a particular information model that you want to be working with in your data visualization. So in this case, hierarchical charts exist within the network frame because hierarchical data, even though it's a very particular structure of network data, is fundamentally network data. It consists of items that are connected to each other. And that's the definition of network data. So it's going to be handled by the network frame. And the way a network frame works is that you can pass it nodes and you can pass it edges. And nodes are items that are connected, and edges are the items that connect them. So in this case, we're going to pass it edges, and edges are literally going to be that hierarchical JSON data set. Now, if you've worked with network visualization before, that might be very confusing to you, because typically edges is an array of source target pairs, what's called an edge list, and nodes is an array of items that those source target pairs reference. And the nodes list is oftentimes optional. And so you wouldn't send edges anything but an array, but now we're sending it an object, and we're sending it this hierarchical object. And that's because under the hood, network frame says, if it's an object, then I'm going to assume that it's hierarchical JSON, and I'm going to process it as such. And that's so that network frame allows you to build whatever kind of charts you want with it, even though it's hierarchical data. So we're going to send it flare data, and we're going to send it a network type called, we'll start with a tree, which is a traditional network data visualization. And now for those of you who haven't watched me live stream before, this is what I do, is I sit here and I say, let's see what that does. Because I can never remember, well, it's not that I never remember. Let me go back for a second. I like to see what immediately makes sense and what doesn't with this library, because it's the only way that I'm ever going to make sure that it works properly. And even though this looks kind of odd, because you've got these rows of dots, this is actually exactly what it's supposed to do. These are nodes from your flare data set, and they're being laid out onto the screen according to the parent-child relationship. And they're being connected by links. The thing is that you can't see the way that they're being connected because we haven't told it how to style those edges. So we can say edge style equals stroke brown. It's easier to remember all of those. And the strokes are gone. Isn't that wonderful? And I've actually, This is funny. So that's not working, and that's not working because I haven't told it what the IDs are. This is a problem I ran into last week. And so this is actually correct. This is what it should be doing. It's just I have to walk myself through these things because I have to make this more sensible for folks. So if we take the node ID accessor, because right, we don't know what the actual individual nodes, if you look and see what's going on, what is happening is React is combining a bunch of undefined connected to undefined undefined edges. And that's because it doesn't know what the IDs in this data set are. It assumes that they're ID. So if this data set, let's see, here we go. If we go look back on this flare data set, if instead of name equals flare, it had said ID equals flare, then it would have worked because that's the default. But instead we have to tell it that no, the name comes from something called name. And sure enough, we end up with a network diagram. For some reason, the top of my network diagram isn't showing. I wonder why that would be. Let's give it a little bit of a margin. There we go. There might be something, obviously, a bug, and I'll go and take note of this bug in front of you. Without a margin, it seems like aren't laying out the root node. I wonder why that would be. It doesn't make sense, and I haven't seen it before, but that's the whole point of doing this over and over and over again, is to humiliate yourself in public and be recorded for all time, because the internet never forgets. However, that said, there's your network. There's your hierarchical diagram. It's not very much code, right, to do a tree diagram. By default, the size of a frame is 500 by 500, so we could change that to, say, 1,000 by 500. And it'll stretch it out a bit, which is nice. If you wanted to, somebody was showing me, I didn't even realize that you could send the R value as a style, the radius of the circle as a style, and it would be honored. Or maybe it won't. You know, that's so strange. I will never understand it. I swear I saw them do it. You can see that this is all the verisimilitude of a real person doing things in real time without practice, because you wouldn't have all of these weird things happening. So there is something in, if I want to make the node smaller, because node size is taken into account with certain layouts, in the network frame that's a node size accessor, and that determines the size of the node. And I will say, just return 2. It's a function that takes the node and returns the value that's going to determine the node's size. It should, and here we'll test things on the fly, it should just take a value also. If it's working properly, good. So I can change the node sizes to whatever I want. So they're not running into each other because there's not much space here. But again, I have a tree diagram, right? You can try the cluster diagram. These are both dendrograms. The difference is that the cluster diagram pushes everything to the bottom. The leaf node, the final node in your hierarchy, is sent all the way to the bottom in a cluster diagram. Now, one thing I could do is I could add some controls here and jump between these so you could see how these animate. But I'm not going to, maybe I'll get into that a little bit later. And that would be as simple as just adding some state and then wiring up the network type to respond to changes in state. It's actually really simple. And I suppose I should do that. Let me just go take a look around at some things before I get to that. Okay. So I'm going to do that, and I'm going to, I think I will go look and see how I'm doing it over here, just to make sure. Just grab the constructor over here. It's pretty simple. Your constructor is honored by the class, the component and it allows you to set an initial state and also to set any sort of functionality where if you wanted to bind internal functions to have the right context and such, you can do that there. So let's go with type. We'll say type equals tree. We will put a button in here. I guess we'll put a select, right? Select. And we'll set up select options. Gosh, this is going to get involved, isn't it? If only it was easy. Oh well, const. I don't think I've done anything that uses state, so I think I should probably do that anyway. Select options equals an array, and so far what have we seen? We've seen a tree and a cluster. Woo. Dot map, and we'll return an option. How does that work? And it's been a while since I've used sort of native HTML elements instead of like we use in Material UI a lot. So I'm going to say value. Well, anybody at home wants to tell me what to do, I will do that. I think you have to say label also, right? Because some browsers honor it and some browsers don't. You probably also have to give it a key, and so I'll give it a key that says, I'm trying too hard, but key that says like a button. And there's my options. That should work. Put those inside of that. Let's see what it looks like. Right, there's my little option. Put this in a different div so that it's not quite a mess. It will never be pretty, but it will be okay. So now I've got a tree or a cluster. Nothing's going to happen when I change that. So on change. What is it going to be? It's going to be E. Oops. There we go. E. And I never remember. Console dot log. E dot target. Is that right? E dot target. Let's see. Link. All right. E dot target dot value. I want to say E dot target value. Let's try that out. Hey, look at that. All right. So E dot target dot value. So instead, I want to say this dot set state. This is just how you set state in React with a React component. You know that. We all know that at home. What do I call it? Type. Type equals E dot target value, and then I go put type over here. This dot state dot type. Let's go see what that does. Rank, and then we say cluster, and it says sure enough cluster. Isn't that nice? It goes from cluster to tree, cluster to tree, cluster to tree. Okay, that's kind of cool, and that's a hierarchical diagram. If we want, we could the way that network types work is the way that all of the data visualization types work throughout Semiotic. So I could send a string, for instance, tree or cluster, which is great. But if I want to send more advanced options, then I send an object of type equal to that string. Okay? So now I'm sending an object of type cluster or type tree, and that allows me to send other parameters. So I could say I could change the projection. I could change the projection to horizontal. So by default, your projection for hierarchical diagrams that allow for that kind of thing, that admit to that kind of thing, is vertical. So top down. We can have horizontal. And it'll just pop it out horizontally, which is nice. And the other option is radial. We can have these pretty radial charts. And again, we can, tree or cluster or tree. Funny, the cluster looks a lot better in radial, doesn't it? I wonder why that is. It's like, I guess maybe clusters are built for the sort of phylogenetic trees of life, right? or something. Who knows? I love it. So anyway, that's how easy it is. That's what I'm trying to tell you. That's how easy it is. And if you wanted to, you could turn on hover annotation, and sure enough, you've got a nice hierarchical chart that you can go and look at the stuff that you know about these things. Now it's only telling you its degree, because it's calculating the degree just as a byproduct of laying it out. You could go in here and adjust the tooltip content, right? Tooltip content equals, it's a function. It's going to take the node. It's going to return some kind of JSX, HTML JSX. Typically, I give it a div. I return a div, and I give the div the class name of tooltip content because I've already written a bunch of CSS rules for tooltip content. You can name it whatever you want. You can write your own rules. You can make it look all sorts of nice. And then you return something inside that div. So we should be able to say like d.name, right? That should work. And now we see it flare, query, if, literal, maximum methods, blah, blah, blah. Let's go to cluster so we can read this a little bit better, right? Ooh, look at that. I'm using data viz. So it's query that has all of these sub-methods. Query.methods. Isn't that an interesting one? Flare.physics, flare.flex.flareviz. Oh, weird. So I guess that's the flex plug. Flare.display.linesprite, dirty sprite, rect sprite. Anyway, look at that. That's all it takes. There you go. You've made your diagram. There are more kinds of diagrams. We'll go back to not declaring a projection. There's a couple of other options. We'll get into those. So what's supported? We've got clusters and trees. Oh, and just so you know, because why not? Network types. Well, we can send it force-directed network. We should be able to send it a chord diagram. We should be able to send it a Sankey diagram. Let's go see. Who knows? I don't know that the chord will work. We'll see. But that's because, like, under the hood, it's processed all the same. It's all in this network frame. So if you take it, you can make it, you can use a traditional force-directed network layout. You could show it as a chord diagram. And the interesting thing, the reason why this looks so crazy with the chord diagram is because chord diagrams are, first, they're not meant for data sets like this. But you've got such small amounts being passed from one end to another that it's a 0 on one end, and that's causing issues with how the chord is actually being calculated because there's no return flow because it's a hierarchical network. So it looks beautiful, but it's really beautiful but meaningless. Like most chord diagrams, I'm going to take a picture of it because it looks so pretty though. Because I take a picture of anything. And then the Sankey diagram, let's go see what that looks like. That should work. Yeah. The nodes are having a hard time being drawn. I wonder why. Why would the nodes have a hard time being drawn? Let's see. Let's go see if there's an actual error, negative value. Again, this could be the result of us not telling it, not giving it a value. I'm trying to think through, like, this data set isn't designed for a Sankey diagram. That said, I would think, and maybe that's what's going on with the chord diagram also. Edge, I think it's edge weight. I'm not going to get too deep into this, but I'll go and test this out so I can explain it a little bit better to folks. We'll see. Nope, just disappearing nodes. Really shouldn't disappear. Why am I getting so caught up in this? I mean, there's two possible issues here. One is an SVG issue that somehow, because of the parameters, the size of the chart or whatever, that it's so small that it's drawing them too small. And I guess that's actually just all it was. It wasn't even a problem of some kind of edge weight accessor or anything like that. It's just that the nodes were so thin based on the calculated value of the size of the, oh, I understand what's happened here. Okay, good. So now I can explain it to you as I explain it to myself. Sankey by default has node padding. I believe it's an 8-pixel default node padding, so that's part of this passing your, I think that should work. Let's see what happens. Yeah, there we go. And what happens is sometimes when you calculate your Sankey layout, when you calculate for the node padding, it actually ends up with a 0 or negative value for the actual size of your individual nodes, which can cause those kind of weird artifacts for how Sankey draws things. So that's all that was happening, and now everything's fine again. And so once I reduce that node padding to something a little more sensible, given the size of the screen that we have, the Sankey layout seems to work just fine. So yeah, Sankey, chord. Chord, of course, will always have problems because chord is about directionality, flow. But I'll take a look and just to make sure. This one part seems a little bit weird to me. But this has no link coming into it. Like somehow the link being drawn into this doesn't exist. These nodes being invisible doesn't surprise me. This is probably a 0 value because it's got no return value. Or it's small enough, again, given the size here. In fact, we can figure that out very quickly. We just blow this up, turn this into a really big screen size, and take a look. Whoa, it's huge. Yeah, this doesn't surprise me. This does. I'll go look at that myself later. I'm not too shocked. I'm not too worried about it, frankly, because it's not the kind of data that a chord diagram is meant to display. So I'm not so bothered that it doesn't immediately display it perfectly. The Sankey would have bothered me more, but once we figured out the node padding, that was that solved that. But here you go, right? You've got your little forest diagram to a cluster diagram to a tree diagram. And that's all available in your network frame with all of those settings, and it's all pretty straightforward. However, what else do we support? We support all sorts of things. We support tree maps. Not really all sorts of things. There's only like 2 more left. But you'll notice if I try to do a tree map right off the bat, the tree map will fail. It'll come back with this garbage, which is basically just about one node. Well, actually, hold on a second. Let me make sure. Because for those of you who aren't aware, tree maps encode parent-child relationship through enclosure, right? So who knows what's going on in here, right? We've got a green node and apparently no children or something. And when you hover over it, because I've got this hover annotation, it's telling me something's there. The reason for that is because a tree map aggregates values in the and displays the aggregated sum of those values. And it can only do that if you tell it what to sum up. Now, if you're familiar with tree map in D3, you pass the tree map, you pass actually the hierarchy function. You pass it a sum parameter. So the hierarchy function isn't exposed here. That sum parameter is just sent as a sum property of your network type. So in this case, what do we want to sum? Well, we want to sum d.value. Hey, wait a minute. Stroke equals stroke. Ha ha ha. You're not. That's not funny. There we go. Go back and go see what that looked like when I wasn't passing stroke equals stroke. Thanks, audience, for not telling me. This works for any of the parameters that are passed to the various network types under the hood. So there's lots of different parameters that I'm not going to try to do sort of colorful ways of passing them through. Basically what it comes down to is if you pass a value and that value if you pass a property in your network type, sorry, not a value, if you pass a property in your network type and that property exists as an accessor function in any of those D3 hierarchical layouts, it'll just pass it through to it so that you can make your tree map have padding, right? Which is super useful. And there's a tree map, and you can sort of scroll over it. It has control points in the hover annotation based on the top middle of every rectangle, which works relatively well. When it comes to labeling, if any of you have been following me on Twitter, you know that I've been playing around with trying to do some good dynamic labeling, and it is tough. It is tough. Anyway, there's our tree map. We'll add tree map to our list. Tree map. Oh, and then we have to go and say now that network type is .state.type. Right? And that's what a tree map is. A tree map, for those of you at home, base mark props, new feature in Semiotic 1.4.1 is base mark props, which sends some, as it sounds like, it sends the same props to all the marks that are instantiated in your data visualization tray. So you can send it transition duration to slow down the transitions, which I think is a nice feature that wasn't available in Semiotic for a long time. So now the transition will be should be a little bit slower. Hopefully, it'll get a little bit slower. Base mark props, transition duration. This might be one of those things that I have to go look up because that looks like it's just as fast as it was. So let's go look up the release notes. To the release notes. Let's see. Semiotic. "36 releases. Blah, 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 blah. Base mark props, transition duration. I'll have to take a look at that. Looks like it's not passing them through. So, another bug. Base mark props and network frame. Okay. So anyway, then you'll just have to pay attention quick. You can see that the tree map is taking all of those original nodes, and instead of indicating whether or not they're related to each other based on drawing lines from parents to child, they're indicating that they're related to each other based on a parent enclosing a child. The last hierarchical diagram that we've got to work with is a partition layout. Partition layout is like a tree map in that it does this aggregated size. See, this thing's gotten too complicated. It's like almost 15 lines of code. I can't even see where my network type is. Partition. Right? And partition layout, probably don't want the padding now. I could do without that. And it's the same kind of chart, and it's just showing connection based on, well, connection, adjacency. So the parent node is Flare, its child is utility. You can tell it's child because it's directly underneath Flare. And then maths is directly underneath util, palette is directly underneath, and then color palette and size palette are directly underneath that, and so on. And so partition is just another way of showing that. And partition is one of those layouts that's amenable to being projected in different ways. So what's my projections? Horizontal. And sure enough, there it is, right? And radial. And like I was saying at the beginning, there is no sunburst in Semiotic. A sunburst is just a radial partition layout. So there's my sunburst. It has terrible labeling right now. So that's the next thing that I'm going to do. I'm going to do a big push to make all of the labeling in Semiotic better. I'm going to make sure that it's the best labeling. Make labeling great again. Let's take a look at all this stuff. Radial tree map, radial cluster diagram. There's no such thing as a radial force diagram, so it'll just ignore that. There's no such thing as a radial chord diagram. There's no such thing as a radial Sankey diagram, though there could be, couldn't there? I should build a radial Sankey diagram. Tree map, there actually is such a thing as a radial tree map. It looks like a Death Star. I don't know that it's useful, but it's there, it exists. And then a radial partition, which is your sunburst. Change this all back to vertical. And go through that one more time. So there's your tree map. Tree map is a cluster diagram, is a force diagram, is a chord diagram. Should probably pull the chord diagram out of there. It's just not good for the data set. People will be surprised. I just wanted to show that it's that easy to go and build a chord diagram. Problem, of course, building a chord diagram is having the right data for it. So a tree map is a cluster, is a force diagram, is a Sankey diagram, is a tree map. I think I already said tree map, so I guess I meant to say tree. A tree is a cluster, is a tree map, is a partition layout. You could spend some time doing color and style based on depth or other factors. You could visualize different kinds of hierarchical network data, build your own, or try to maximize whether or not you wanted to display leaf node structure or parent node structure. Those are the choices that are involved with hierarchical layouts. You could, if you wanted to, use different edge types, right, to display the information. I think that built-in, let's see something. I think this should just work. We'll see. Taffy. I built in support for a bunch of different glyph edges that I made. Oh yeah, that does work. And so this is fun because you can. There's a few. So a long time ago, I guess I should use my words. A long time ago, I built a library called D3 Glyph Edge. And D3 Glyph Edge was built for traditional force-directed network layouts. I go to the live example. But you know, these are useful for all sorts of different network layouts. I don't know why the performance is so slow right now. So there's all sorts of different kinds of glyph edges. So a glyph just means complex graphical shape. And edge is just the connection between two networks. So we have this half arrow, comet, taffy, ribbon, arrowhead, offset, and nail. All of these are supported as just words in edge type. It's just strings in edge type, except for particle and offset. Particle takes a bit more effort under the hood to get working. Offset's a special case. Oh, actually, offset might work. I'm thinking of parallel edges. I'll check and see if offset works. I can't remember. Let's take a look. So anyway, arrowhead, which means we should be able to say half arrow. In this case, because they're filled, we don't really need to do a stroke as black. We can do a stroke as none, because that's making them even heavier. Hey, wait a minute. That's not right. That's my nodes. Them's my nodes. Edge style, stroke none. There we go. Or here, we'll fill. We'll just change that to fill. Fill, like the groundhog. Okay, so half arrow. Arrowhead. If you like those little archy lines that became real popular with Gephi, in these cases you would not want them filled. I don't think that this is probably a good choice for, I don't know, that looks great, doesn't it? I take it all back. It's wonderful. It's the best. I have made networks great again. Taking a picture. Where was I? Line arc, arrowhead, half arrow. Let's see if those offsets work. I don't know that they are supported. Something tells me not. No, that looks supported. It looks like it's slightly off to the side. Because it's in one direction, right? An offset edge is this way you can have them in one direction versus another. I'll have to take a look at that. That's another thing to look into. Offset edges. And what was the other one? Oh, right. There's no difference between comments and lines except that it's exactly the same generator. It's just pointed in one direction versus the other. Let's go back to Phil Brown, stroke none. There we go. So in one direction, I guess we should probably give that a stroke so you can, or here, we'll do this fill opacity. So you can see the overlapping. There we go. Comments, nails are in the other direction. Right? And then taffy is fat on both sides and thin in the middle. Oh, and there's a ribbon that's just a fat with no variation. And that's the edge support that it comes with. I think I'll leave this as arrowhead if somebody sees this library later or sees this example later. So yeah, that's how you make hierarchical layouts and use all the cool arrowheads and whatever that are available in Semiotic. If you have any questions, be happy to answer them. Otherwise, I think I'm going to stop there. I'll try to edit this, tidy it up for the permanent YouTube video. And otherwise, I'm going to push this example up to the Semiotic examples repo. And that's it. That's how you make hierarchical charts in Semiotic. I hope this was useful for you. If you have any questions, feel free to reach out to me on Twitter or on the D3 Slack or via email, or feel free to leave bug reports or feature requests on the GitHub repo, the Semiotic repo. Thanks everybody, and hopefully I'll see you next week. Bye.